What's up guys, so it's me again, and for this video, so we're going to discuss, or I'm going to tackle about the IP address and the number system. So IP address, or the internet protocol address, is a logical numeric address which is assigned to hardware like computers, switches, routers, and other devices that are part of the TCP or the IP-based network. So the IP address, it helps for uh, it helps to identify the devices. Like for example, it is like the city address, or for example the uh, address of our houses. So for example, we have a delivery, so we need to give a address for them to know where to deliver the package. So it's also like that. So when, for example, when we search in the URL, like for example is facebook.com, so the www.facebook.com, so the network will know which device asked for that information. There are two versions of the IP address. One is the IP version 4, which is the older version, and consists only of 4 billion unique IP addresses, and it has 2 raised to 32, and uses 32 bits. So IP version 4 displays IP addresses, or displays addresses in decimal format. So the other one is the IP version 6, which is which provides a larger number of addresses, and it has 340 trillion unique IP addresses. And so their IPv6 have benefits. So first is there's no collision caused by the private addresses. It helps to auto configuration, efficient routing, easier administration, and built-in privacy. So IP version 6 display addresses into hexadecimal format, like what you see in the screen. So now let's discuss about the number system. So number system, it is a technique to represent numbers in the computer system architecture. So every values that are saving or getting into or from the computer computer memory has a number, or defined by number system. So there are 4 parts, or 4 parts that supports the computer architecture, which is the binary system, the octal number system, the decimal number system, and the hexadecimal number system. So the first is the binary number system. So it consists of 2 digits, which is 0 and 1, and it is also known as the base 2 system because of it only consists of 2 digits. Then there is the octal number system, which consists of 8 digits, which is 0 to 7, and also known as base 8 system because of the 8 digits. So next is the decimal, which is consists of 10 digits that are 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the last one is the hexadecimal number system, which consists of 16 alphanumeric values from 0 to 9 and A to F. So A to F is represent as the 11 to 15. So decimal plural using successive division. For example, we have 348, base 10, base 10. So 348 decimal, which is base 10. So, and we're going to convert it to binary. So we're going to use 348 divide 2 is equals to 174. Remainder is 0. Then 348 by 174 divided 2 equals 87, remainder 0. And 87 divided 2 is equals to 43, remainder 1. 43 divided 2 is equals to 21, remainder 1. 21 divided 2 divide 2 divide 2 equals 10, remainder 1. And 10 by 2 is equals to 5, remainder 0. 5 divided 2 equals 2, remainder 1. And 2 divided 2 is equals to 1, remainder 0. 1 times 1 divided 2 is equals to 0, remainder 1. So the answer will be, so when we're getting the answer, or when we're going to convert, we read the numbers upward. So the answer will be 1 0 1 0 1 1 1 0 1 0 0 0. So that is the binary of the 348. So let's proceed to decimal to octal. So 348, we're going to use again the 348 in converting decimal to octal. And because if octal is base 8, we're going to divide 348 divide 8 equals 43, remainder 4, then 43 by 8 is equals to 5, remainder 3, and 5 divided 8 is equals to 0, remainder 5. So we're going to read it again upward. So the answer will be 534 base 8. Then let's proceed to decimal to hexadecimal. So we're going to use again the 348, and now we're going to divide it by 16. So 348 divided 16 is equals to 348 divided 16 to 21.75 or equals to 21, remainder 12. So in getting the remainder, we're going to multiply the 0.75 times 16 equals 12. So that is the remainder. Let's continue. So 21 divided 16 is equals to 1.3125 or equals to 1, remainder 5. And 1 divided 16, so this will be 0, and then remainder 1. So the answer will be, so we're going to again to read it upward. So the answer will be 15, 12. So 15 is or equals to 15 C. So the answer will be 15C. So and when we convert decimal to binary, to octal, and to hexa, we use division. So now, if we're going to convert the octal, the binary, and the hexa to decimal, we're going to use multiplication. So, for example, binary to decimal. So we're going to use 1 0 1 0 1 1 1 0 0 0. So we're going to use multiplication. So this is binary. We're going to times each digit to 2 and with the exponent. So 1 times 2 raised to 8 raised to 8 plus 1 times 2 raised to 7 1 times 2 plus 0 0 raised to 7, then 1 times 2 raised to 6, 1 times 2 raised to 5, this will be 0 0 plus 1 times, then this will be 0, this one is 0, then plus 1 times 2. So we're going to put first we're going to put the exponents later. Plus 1 times 2 plus 1 times 2 plus 0 times 2 plus 0 times 2. So the last one is raised to 0, then this is raised to 1, then raised to 2, then raised to 3, then raised to 4. So the answer will be so 2 times 2 raised to 8 is 256 times 1, so still 256 plus 0 times 2 raised to 7, so it will be 0. Then 1 times 2 raised to 6 is 64 plus 0 times 2 raised to 5 is 0, and then 1 times 2 raised to 4 is 16. And 1 times 2 raised to 3 is 8. That's 8. Then 1 times 2 raised to 2 is 4. Then 0 times 2 raised to 1 is 0. Then 0 times 2 raised to 0 is 0. This equals to 348 base 10. So for octal, octal to decimal. So we're going to use 534 base 8. So we're going to multiply this by 8 because octal is base 8. So each digit should be multiplied by 8 and with the exponent. So first is 5 times 8 raised to 2 plus 3 times 8 raised to 1 plus 4 times 8 raised to 0 equals, so 5 times 8 raised to 2 is 320 plus 3 times 8, 3 times 8 raised to 1 is 24 plus 8 raised to 0 is 1 times 4 is equals to 4. Then 320 plus 24 plus 4 is equals to 348 base 10. Then the hexadecimal to decimal. So 15C hexadecimal to decimal. So we're going to use 15C. So we're going to first convert this to numbers. So it will be equal to 15 and 12 because C is equivalent to 12. Then we're going to multiply each digit by 16 with exponent. So 1 times 16 raised to 2 plus 1 plus 5 times 16 raised to 1 plus 12 times 16 raised to 0 so raised to 0 plus 16 squared is 256 times 1, so it's still 20 plus 16 raised to 1, 16 times 5 is 80 plus 16 raised to 0 is 1 times 12 is 12. So equals 256 plus 80 plus 12 is equals to 348 base 10. So now we're going to subtraction in converting a decimal to binary. So decimal to binary. So in doing this, we're going to use the exponent of 2. So this will be the 512, 256, 128, 64, 32, 16, 8, 4, 2, and 1. So for example, we're going to use again the 348. So base 10, so we're going to convert it to binary. So we're going to find the smallest amount, or the less than 348. So the less is 256. So 348 minus 256 is equals to 92. So then we're going to find again the less than 92. So 92 minus, so the less than is 64. Then 64, 92 minus 64 is equals to 28. So 28, then we're going to find the digit that is less than 28. So minus 16. So 28 minus 16 is equals to 12. So we're going to find the digit that is less than 12, which is 8, equals to 4. Then we're going to find the less or the equal amount or digit of this, which is 4. 4 minus 4 is equals to 0. So we use 156, 92, 28, 256, 64, 16, 8, and 4. So in converting to binary, so we're going to assign values in the values of the exponent. So 512, so we didn't use 512, so this will be 0. Then 256, so we use 256, there will be 1. Then 128, we didn't use 100, this will be 0. Then 64, we use 64, then will be 1. Then we will use 32, then we use 16, and we use 8, and 1 and 4. Then we didn't use the 0, the 2, and the 1. So this will be the binary of 348. Then I'm going to convert hexa to octal to hexa. Octal to hexadecimal. By doing so, we're going to, for example, we're going to use 213 base 8. So doing so, we're going to so like first 2, 1, 3, and we're going to we separate this into 3 groups, which and then we're going to use the value of exponents, which is the first here is, so we're going to use 1, 2, 4, and 8. And here is 1, 2, 4, so it should be by 3s only because it is octal. So 2 and 4, so right, so by it, to have 3, we're going to look for the numbers in these 3 given numbers, so to make the 3, so 2 plus 1, so we're going to convert octal to hexadecimal. Octal to hexadecimal. So in doing so, for example, we're going to use 213 base 8. So we're going to separate it into 3. 2, 1, 3, and then we're going to use the values of exponents, the 1, 4, and the 1, 4, 1, 2, 4, 1, 2, 4, 1, 2, and 4. So we're just going to use 3 because octal, we use octal 3 bits in octal. So we're going to use zeros and 1 in so we're going not so this is 2, so we're gonna use the 4, so we'll assign 0, then we'll use the 2, so 1, then we're not going to use the 1, so it's going to be 0, then we're not going to use the 0, the 4, and the 2, so we're going to use the 1, then we'll assign the 1, then we're not going to use the 4, but we're going to use the 2 and the 1, so we assign 1. So this will be the binary equivalent of 213 15. So we're going to convert it to hexadecimal, then we're going to cut it into 4 digits. 1, 2. So we're going to add 3 zeros here just to complete the. So we're going to use again the values of exponent. So 8, 4, 2, 1, then 8, 4, 2, 1, then 8, 4, 2, 1. So since the assign here in number 1 is 1, so we're going to use 8, and we're going to substitute the value. So we use the 1, the 2, and the 8. So the answer will be 11. The answer will be 11. Then here, we only use the 8. So substitute 8 with 8. Then here we didn't use anything, so this will be the value of 11 to hexa is equals to 811. So but the value of 11 in hexa is letter going to, so 8, and so the value of 11 in hexa is equals to B. So the 213 is equals to 8B. So that's all for this video. So thank you for watching.